So in this video we're just going to have a look at a few further examples for measuring enthalpy changes using calorimetry. So in this one, what we're going to do is find the enthalpy change of neutralisation. 50 centimetres cubed of 1 molar hydrochloric acid was put in a polystyrene cup and the initial temperature was taken, and then 50 centimetres cubed of sodium hydroxide was added and the temperature rose by 6.75 degrees. So let's just draw a picture of that. We've got our polystyrene cup here. Okay, we've got some liquid in it, we've got our thermometer in it, and we have got in here 50 centimetres cubed of HCl and 50 centimetres cubed of NaOH. And the temperature rose by 6.75 degrees C. So delta T equals 6.75 degrees C. So when we do a calculation like this, we're going to have to make a couple of assumptions. First of all, we have to assume that hydrochloric acid and sodium hydroxide are just like water. Well, the majority of the solution is water, because it is a solution dissolved in water, but it's not going to be perfectly true that the density is 1 gram per centimetre cube, but we're going to assume that. So in this case, the total mass of our solution is going to be the sum of the two solutions. The temperature when the temperature rose, there was 50 add 50 centimetres cubed, which is 100 centimetres cubed, and we're going to assume that the density is 1, so that's 100 grams. And we're going to assume that, because it's mostly water, that the specific heat capacity of water is acceptable. So let's have a look what it is we're trying to measure. We're trying to measure the reaction between sodium hydroxide and hydrochloric acid. So pause the video and finish that equation. That should be relatively straightforward. Remember, we were said that the mass of our solution is our total mass, which we've already worked out is 100 grams. So step 1, calculate Q. Q equals mc delta T. So the M is the mass of the solution. The specific heat capacity will always be given to us in the question, and our delta T was 6.75 degrees C, which remember is the same in Kelvin when we're just talking about a difference. So type that on your calculator and work out an answer. So 2821.5 joules. Remember that one's in joules. Calculate the number of moles. Now it's telling us to do hydrochloric acid here. In this case it wouldn't matter whether we did hydrochloric acid or sodium hydroxide because they have the same number of moles. But we may come across an example later on where one of these two reactants is in excess. There's more of one than the other in terms of moles. We would always use the limiting one in our calculation because it limits the amount of heat that can be produced. But here, since they're identical, it doesn't really matter. Now, hydrochloric acid is a solution, so how do you calculate moles of a solution? Pause the video, look at the data and see if you can calculate it. So since it's a solution, we're doing moles volume times concentration, and since concentration is in moles per decimetre cubed, we turn our volume into decimetre cubed. So step 1, find Q. Step 2, find moles. Step 3, delta H is Q over moles, but remembering that our Q has to be converted into kilojoules. So 2821.5 joules, turn it into kilojoules, because we want our answer in kilojoules per mole. Divide by moles to find it per mole, and you get 56.43. But we haven't finished because we haven't done step 4, which is add a sign, and then we'll also go for the appropriate significant figures, which looks like it's about 2 here, because of the data, minus 56 kilojoules per mole. Why did I choose a minus? Because the temperature rose, so it must be an exothermic reaction. So we've got 2 more problems on this page. I want you to have a think through. Problem 1 is like the example in the first video. Problem 2 is similar to the example in the second video. What I'd like you to have a do is have a go at problem 1 yourself now. Remember the 4-step method. Find Q, find moles, find delta H, get the right sign. So see if you can work your way through this problem number 1. Pause the video and have a go now. So there we go, let's have a look at the steps. Step 1, find Q. Remember it's the water that rose in temperature, so it's the energy of the water. So 100 grams of water, 64.9 temperature change and times by 4.18. How many moles of fuel did it take to make that change? So we work out the moles of fuel, mass over MR. We were given the formula of propane, so there's no problem getting the MR there. And then delta H is Q converted into kilojoules and divided by moles. And then step 4 is add the correct sign, and the question said give our answers to 3 significant figures. So I've given it to 3 significant figures. So let's have a go at problem 2. So 3.53 grams of sodium hydrogen carbonate was added to 30 centimetres cubed of hydrochloric acid. So we've got this beaker, and in it we've got 30 centimetres cubed of 2 moles per decimetre cubed HCl. We've got a thermometer in that, and the thermometer's measuring the water part of it. Okay, and the temperature delta T is 10.3 Kelvin. It fell 10.3, but it's still 10.3 as a change. We added in a bit of 3.53 grams of sodium hydrogen carbonate. Okay, so assume that the density of the solution is 1 gram per centimetre cubed. So assume it's just like water, and the specific heat capacity is 4.18. First thing it asks you to do is work out which reagent was in excess. That's going to be important because whichever one is not in excess, is limiting, is the one that determines how much heat can be given out or taken in. So we do not use the excess one in our calculation. So to work out which is in excess, we work out moles of each. We're going to do it in a slightly different order here. So can you pause the video now and work out the moles of sodium hydrocarbonate and the moles of hydrochloric acid? Different methods because they're different types of chemicals. So you should have got, for the solid, mass over MR, and for the solution, volume times concentration, and you get those two numbers. So we can say that there's more HCl than there is NaHCO3. So the HCl is in excess, okay? Which means that the maximum amount of moles that can react, the limiting one, is the sodium hydrogen carbonate. So we're going to use the moles of the other one because that's limiting our reaction. So now we're going to go back to our method. Step 1, calculate Q. Remember Q equals MC delta T. And here the thermometer is just measuring the solution, and there is 30 centimetres cubed or 30 grams of liquid times 4.18. And our delta T, doesn't matter that it goes up or down, we take account of that at the very end, it's 10.3. So that's 1291.62 joules on my calculator. I've already done the moles bit, so I can skip straight to delta H, but I need to make sure that I turn my Q into kilojoules and I divide by the right moles. So 1291.62 into kilojoules divided by the limiting amount. And type that on your calculator, you get 30.8 kilojoules per mole. And step 4, remember, always last thing to do is think about the sign. If the temperature rose, then it would be exothermic, but in this case the temperature fell, therefore it's endo, which means it has a plus. And the mathematicians among you might say, well, I don't need to put a plus in if it's positive. But in this example, the plus means something chemically. The plus tells the chemist that heat energy was taken in from the surroundings, so the chemicals gained that 30.8 because they took it in from the surroundings. So that plus is very important.